My slide is visible to you?
Yes.
Okay. Yeah, so good evening everyone. Today we are going to discuss about the live session 12, where we will be mostly solving the problem regarding the first we'll discuss about the polarization, modulated sensors, and sensing properties and application, and after that we'll go for the question answer session. My voice is audible?
Yes, sir.
Okay. So we have discussed till now amplitude, phase, and wavelength modulated optical sensors. Now we are going to discuss about the polarization modulated optical sensors. In this, you can discuss, you can understand that the polarization is totally different from the previous modulated sensor, where we can physically also can be distinguish that which wavelength by seeing or by spectrometer or photodiode. Um, Similarly, the phase also can be measured quickly, and the amplitude also intensity can be measured. But what about the polarization? Polarization is quite difficult to measure, but if it is elliptical or circular polarized light, and also it can be it can, but the advantage is it can carry much more um, uh, intense information compared to other optical sensors. Obviously not like a phase, but similar to that. Also it can carry the very high dense information about uh, the application, which is going to be which are going to which we are doing, it's happening. So you can see here that the um, x, y, and g graphical representation scheme I have shown, and in this you can see that y-axis ey, and x-axis there is a ex vector is there. Then this is the resultant polarization, which is towards the y-axis, and horizontal component is the cyan one, and the vertical component is the magenta one. I'm teaching the pen. Yeah, this is magenta one, and the polarization modulated sensor is shown in the amber one, the component which is polarized in that uh, for this electromagnetic radiation, and the propagation direction is z-axis. So one of the component is oscillating in x-axis, and another component of the electromagnetic radiation is oscillating in y-axis, and the resultant is propagating towards the z-axis. We have discussed about various sensing modulation. One the um, mm, we can read amplitude modulation, phase, wavelength, and polarization, which we are going to discuss now. So in amplitude there will be we are dealing with amplitude obviously. Then phase, again there is a phase difference, phase mismatch. So interferometer we are going to use, and we are using it. And in the wavelength there will be a difference in the change in the wavelength, as we have discussed in the last 3 weeks. It was totally intense discussion about the wavelength modulated sensors. Now we are going to discuss about the polarization one, where we are dealing with the electromagnetic radiations polarization axis as a modulation, and for the sensing application. So the tracking the spatial evolution of electric field vector to quantify external perturbations is going to be a study, or it going to be this modulation only going to be used for the sensing application. So you can see here that x and y axis are the oscillation of the electric and magnetic field, and if it is a circular polarized light or plane polarized light, it depends on the various condition, and propagation direction is z. Let's move towards the polarization types. So the first polarization type is linear polarization, where the oscillation will be happen in the one plane. uh, the total electric field vector will be in the one axis, while in circular polarized light it will be having the vector will rotate with the axis x and y, so it will not be a constant vector. While elliptical polarization, there will be this vector will be in a elliptical manner, it won't oval shape, it won't be like a circular polarization. So it is the linear polarization. Using the linear polarization we can uh, achieve the circular polarization, also we can achieve the elliptical polarization. Depends on the which kind of wave plate we are using, quarter wave plate or half wave plate, and the combination of both. Now in this uh, slide, the uh, the mapping of the changes of the Poincare spares is mentioned, where you can see that the horizontal, linear, vertical, and elliptical state, quarter wave plates, everything is shown here in this particular sphere. So any perturbation to the optical fiber forces the polarization state to mitigate across this surface. So everything will be in this surface only, whatever mentioned. uh, yeah, so there is a problem with the, again, like on phase modulation there was a problem to detect it. The directly photodiode can't detect the phase modulated signals. Similarly here also, the polarization modulation can't be detected by the photodiode directly. You can see here the physics behind it, the vector rotation, the external state is given here, and because of that there is a perturbation in the signal, and this perturbation can't be detected directly by the photodiode. It's like a polarization blind. It's totally not understanding what is happening, only it can detect the intensity. So the hardware is not capable to detect it, so it will only detect the intensity output. So here an optical demodulator is strictly required to translate spatial rotation into the measurable intensity variation. So again, this optical demodulator we have discussed previously also, how we are doing the phase into intensity or amplitude, and after that the photodiode is detecting that. That has been done previously as well. Moving towards the next thing, which is the detection part only. So how it is going to be detected? So uh, there is a baseline approach, which is a Mel's law, where this equation you can see the P transmitted is equal to P naught cos square theta. So the incident light with the polarization intensity will propagate through this rotating polarizer, and there is a photo detector which will be detecting the P transmitted through the polarizer. So the polarizer can be, it's a rotating polarizer, so it can be rotated from the minus 90 degree to plus 90 degree, and the intensity is coming at at 0 degree it is a maxima, and at 90 degree, both plus 90 degree and minus 90 degree is a minima. So this is how the transmitted power can be can be um, uh, calculated, or can be um, um, the detector will detect like this. So here you can see that the dead zone at 0 degree and 90 degree derivative is 0. So the minimum sensitivity to small rotation. So it's like a at 0 it's a maximum and 90 it's minimum, and the sensitivity is very small with the rotation, so it's coming like a broad intensity modulation uh, while rotating. And this is the DC background where high baseline power masks micro perturbation and into the short noise. So now we have discussed how we are going to discuss how we are going to sense the transmitted polarized light or the incident light from the sensing for the sensing application through the rotating polarizer to the detector, and detector will detect P transmitted one. But there is a again there is some problem with that. Every time you can't understand that why, because of the intensity or because of the polarization this intensity is decreasing, the P naught. So that can be only um, um, eliminated by using the by using the beam splitter and two photodiodes. Excuse me. Just a second. Okay. So here is a beam splitter which is Glan Townsend polarizing beam splitter. It is um, uh, splitting the polarized part into two direction, where the photodiode 1 is um, getting the reflected beam of the polarized light, while the photodiode 2 is getting the sine part, which is a transmitted beam of the uh, polarized light. And according to this, whatever is they are getting, there is a sine and cos part of both intensity, and because of this because of the intensity is different um, during the polarization can be uh, it is detected it is forwarded to the differential amplifier, where this differential amplifier um, uh, detects the output based on the intensity which is um, reflected towards the photodiode 1 cos part minus the reflected part transmitted part towards the photodiode 2 part 2 port 2. So this is approximately cos 2 phi, and because of that if the DC background is 0, then it can be easily understandable that the intensity is in the cos 2 phi, how much the intensity angle is there, and what is the polarization for that, the intensity what is the polarization for the information sensing modulated signal can be um, and detected by the photodiode easily. And this simultaneous orthogonal detection eliminates the DC background completely. So this is the optimal architecture for polarization diversity. Now the there is a biasing for maximum sensitivity, and this is the equation di upon d phi is equal to minus 2 rp naught sine 2 phi, and the spectra graphical representation of spectra shows that the normalized power p by p naught and rotation angle from that we'll get that at precisely pi by 4 the derivative reaches absolute maximum by launching input polarization at 45 degree. The sensor captures the largest possible current change for the smallest possible physical perturbation, and you can see here how it is happening that. Okay, so this is the biasing for maximum sensitivity. Moving towards the next thing, which is the real world application, how we are using it in a real world application. For that the fiber optic current sensor we are using, and this is very uh, sensitive and very useful nowadays, where the leak from the wire or something, electrical wire can be easily um, um, detect or detected, or it can be easily measure that where anywhere the leak is there or not. So the measuring current from 0.01 ampere to kilo ampere linearly without Hall effect calibration issues. The magnetic field mapped directly to the fiber's optical axis. This is one. B phi is equal to mu I upon 2 pi r can be used for this. So this is the real world application of this polarization dependent application. Moving towards the next thing, which is the mechanism behind it, whatever we are discussing, the mechanism, what is the mechanism? So you can see that the Faraday rotation is also happening in that. So the theta of the rotation angle inside the fiber is nothing but the vertic constant into magnetic flux into length, and this worded trade-offs with two things, which is a material, which is one tag crystal and another is silica glass. So worded constant for tag crystal is 1.16 minute per centimeter inverse. I don't know what is this unit actually, I need to check. And the silicon glass also the similar, but it's very less worded constant, 0.01 minute per need to check what is the unit here. And the length required is centimeter and hundreds of meter for the silicon glass. So this is the core mechanism behind this FOCS. Now discussing about the engineering hurdle, what are the issues facing by engineering this fiber, optical fiber for the FOCS. So there will be a environmental bifringings also. Non-reciprocal force Faraday effect, it is like this, but reciprocal force stress induced bifringes are random, it's not a unidirectional. So a tiny theta rotation from a magnetic flux easily swamped by random stress induced bifringens caused by industrial vibrations. So that's why this is the the real hurdle for this application, or this this modulated sensing. How it can be fixed? So the solution for this is reciprocal reflection configuration, where the step 1 is the forward part, where the Faraday angle and the noise angle will be addition will be there, and then step 2 the Faraday mirror, a perfect reflection, and that is propagating again the return path, where the continuous Faraday angle and the unwind noise also will propagate, minus unwind noise, the noise angle. So the final output will be 2 theta Faraday signal and zero noise. So initially there were noise, and then after unwind it will be having the negative noise, the negative noise will be reduced, and that's why this reflection geometry is very important here. Whatever noise is coming, that will be cancelled, automatically cancelled because of the unwind noise, this noise angle, and the Faraday will multiply and it will become double of that angle will double of that. Now that scaling, the spatial scaling, how the polarization OTDR works. So the optimal time domain reflectometry merges with polarization. So the Rayleigh backscatter returns elliptically polarized light, mapping localized stress, vibration and field across kilometer of continuous fiber via time of light. And this is the graphical representation for that. The pulse light is coming towards this throughout the fiber, and this way it's propagating. But Same time, the relay backscatter light also uh, propagating backward, and this at the strain point, there will be a polarization difference. This place it will be having the strain impact point and having the elliptical polarization in the some other random direction, and which is not matching with this particular point where the strain impact point has the another uh, polarization. The ultimate optical sensor metric has been shown here, where the modulation or modality has been mentioned in the first column, which are amplitude, wavelength, phase, and polarization, and the cost, sensitivity, noise, primary application, everything is mentioned. You can see here that the amplitude modulation's cost is quite low, sensitivity is also low, it just deals with the intensity, and the noise is quite high, and which is used for the gas absorption spectroscopy, which we have discussed in week 1, week 2 content. Then we have gone for the wavelength based modulation sensing application, where the cost and complexity is medium, it doesn't beyond the limit or beyond the expensive limit, and the sensitivity also in the medium range, and the noise is very high to strain and temperature. In simple perturbation also can change the tune the wavelength by few nanometers, and this used in the fiber break gratings. Next one is the phase. Cost and complexity is quite high, but sensitivity also very high, extreme. The noise and the noise and robustness is mentioned as very low. Phase noise will be very low and the highly susceptible, so it can be used for the so many application, including the gyroscope sensing, which is everywhere all over around the world, using for the airplane aerospace technology, aviation industry. Then the last one which we have discussed in this week, which is a polarization based. The cost and complexity is very high, but the sensitivity is also a very extreme level, and the noise is high. With reflection it can be fixed, and it can be an alternative for the phase, but not for the amplitude and wavelength, which has the limitation with their own things. And the primary application is magnetic field and current, so it can be used for the leak of the current from the tiny micron milliampere current to few kiloampere current can leak. It can detect the leak of the current. And the final note is sensor selection is fundamentally a trade-off between the deployment simplicity, like an amplitude, and absolute precision, phase and polarization. So here is the diagnostic flow chart, and for selecting the right sensor. So first thing is scope of measurement. So if it is a distributed, then the frequency, is it a frequency or not? If it is a frequency, then frequency based, then high or static, which one which is the your choice. So if it is high, then you need to go for the dash or phase based dash, and the frequency is static, then wavelength OTDR is the perfect choice for this. If you are talking about the localized point wise sensing, then is it a target variable? So if it is a variable like intensity or concentration, then the best sensing modulation is amplitude modulation, and which can be used for the differential absorption study. And if it is a variable target is rotational or magnetic field which is fluctuating, then the best sensor modulation is polarization for the sensing, and it can be used for the Sagnac and Faraday. Okay, so here I have finished all the discussion about the polarization based modulation and its application in sensing. Now we are going to discuss about the question answer session. Before that, if you have any questions or any doubts, you can ask me. Then we'll move to the question answer session. Jenny, if you have any doubts, you'll ask me.
Yes, sir. We'll go to question answer.
Question answer. And then
Okay.
give me some time. I'll just have water and I'll be come back quickly.
Okay.
Yeah. Okay, so let's start question answer session. Uh, on screen you have, I think this is video is on. It's not going there. Now, yeah. Okay, so the first question is, in the general expression of an electromagnetic wave propagating in a z direction, how is the state of polarization determined by the component of the electric field in the transverse plane? Option A, by the sum of the magnitude of the x, y, z components of the electric field. B, by the ratio of the amplitude ax and ay and the phase difference phi between them. C, exclusive by the angular of frequency omega and the propagation constant beta. and D by the absolute phase of the wave at time t is equal to 0 and z is equal to 0 only. Provide your answer.
Option B.
Okay, let me check. Just a second. Huh? Where is the password? Yeah, so you are talking about option B. Yeah, so in general, the expression of the electromagnetic wave propagating in the z direction, however, the state of the polarization is determined by the component of the electric field in the transverse plane by the ratio of the amplitude ax and ay and the phase difference phi between them. Yes, it's correct. Then that's how. Let me take the pen. So you are correct. We are taking the ratio of the amplitude ax and ay and the phase difference phi. This is the correct answer for that. The next question: which condition must be met for a wave to be classified as having right circular polarized light RCP according to the conventions discussed? Option A: the amplitude Ex and Ey are equal and the phase difference phi is minus pi by 2. Option B: the phase difference phi at 0 and the amplitude Ex and Ey are equal. Option C: the amplitude Ex and Ey are equal and the phase difference phi is plus pi by 2. Pi by 2. Option D: the phase difference phi is pi and the amplitude Ex and Ey are unequal. Let me know your answer.
Option A, sir.
Option D.
A.
A. Yeah, so it's correct. Actually, here is a thing. The amplitude Ex and Ey are equal and the phase difference phi is minus pi by 2. It can be plus pi by 2 or plus minus pi by 2, but we are talking about the phase shift in really right circular polarization. Um, the right hand counterclockwise rotation relative to the propagation in the direction of negative sign. So the negative sign denotes the right hand rotation. So that's why the minus pi by 2 is correct. And we know that this circular state requires equal orthogonal amplitude. So that's why this amplitude Ex and Ey are equal in the circular polarized light. If it is a linear, then it will be having the it will not be having the equal Ex and Ey. It might be uh, uh, it will vary. But if you have elliptical, so this Ex and Ey will not be totally equal. One part will be very high, one will Ex or Ey won't be perfect equal. For the circular only it will be equal. Okay, so both will be equal. Yeah, so your answer is correct here. This is not correct because the difference of phi is 0 and amplitude are equal. No, it's not correct. Phase difference is phi is 0. No, it's not 0. Okay, so moving towards the one more thing here, the plus pi by 2. Yeah, because the right side circular polarization we are going to we are discussing, so that's why it is not correct. And the last one is also not correct. Both are unequal. It's not possible in circular polarization. On a Poincare sphere representation, where are the linear polarization states located? Distributed through the upper hemisphere only. Option B, at the north and south poles. Option C, along the equator of the sphere. And option D, concentrated at a single point on a prime meridian.
Option C.
Option C, at along the equator of the sphere. Okay, yeah, you are correct. So this option C, what it represents is the equate uh, um, the along the equator of the sphere, all possible linear polarization represents, while the pole represents circular polarizations, and in between area represents the elliptical states. So this is the correct answer. It was quite easy. What is the primary function of a quarter wave plate in manipulating polarization state? To increase the total intensity of the light by aligning the phase of all propagation modes, to introduce a pi by 2 phase shift between two orthogonal components, potentially converting linear to circular polarization. C, to rotate the plane of linear polarization by a specific angle without introducing ellipticity. And D, to block one of the orthogonal component to ensure the light is purely linearly polarized. Which is the answer?
Option B, sir.
Option B.
B.
D or B?
B, sir. Pi by 2 phase.
Okay. Yeah, you are correct again. So this quarter wave plane manipulating polarization state, to introduce a pi by 2 phase shift between two orthogonal component, potentially converting linear to circular polarized light. Yeah, that's the correct. So circular polarized light, how we are converting it? Using two orthogonal components, or maybe two linear polarizations. So it may be for a while like this, for second time like this. So the amplitude will change in the direction, and that's why we are getting this polarization, circular polarization, like this is the proper. If you are seeing the light, the polarization from the origin towards your side, the g-axis is your side pointing, then this is how it happens. And quarter wave plate introduce a pi by 2 phase shift for this. According to the uh, okay, according to the Miller's law, if the polarization is oriented at at an angle theta relative to the incident linear polarization, the transmitted power P trans is proportional to. This one we have already discussed, Miller's law. Answer?
Option A.
Option A. Option A. P trans is equal to what we have discussed. P naught.
Cos square theta.
Cos square theta na. So option B na.
2 theta, sir. Cos 2 theta. Option D, sir.
Option D है.
हाँ.
Let me check. Cos square theta. No, you are talking about this one. No, no, just a second. Might be you confused with this one, the polarization diversity. No, we are talking about the Miller's law for the baseline approach. P transmitted is proportional to cos square theta, not cos 2 theta. Cos 2 theta is for the differential uh, uh, intensity detection. What is coming in the reflected geometry and what is coming in the transmitted geometry, photodiodes. So that is totally different. Okay, so it's a cos square theta. This is the correct answer for that. It's totally my I'm not able to write properly on the screen. I try to write like this. P trans is equal to P naught cos square theta. Okay, going towards the next question. Why is the polarization diversity scheme using a balanced detector preferred over a single analyzer for sensing application? Option A, it provides a differential output that eliminates the DC background and doubles the sensitivity to small rotation. B, it allows the system to measure the absolute wavelength of the light simultaneously. C, it ensures that the light remains circular throughout the entire fiber length. D, it eliminates the need for a bifurcation material in the sensing region. What's your answer for this? Why we use this balance detector? Any idea? Any answer?
Not sure.
Huh?
Not sure.
Not sure. Just guess it. Balance detector we discussed already. Maybe I should recap you. Where is it? Here. Let's see that. So the correct answer here is this one. So the sensitivity doubles and the DC backgrounds become 0. For that, this is the correct, I think. DC background 0 and the intensity doubles here. You got it?
Yes.
Yeah. So it's you can say that using these two things we can sure it that whether it is a which polarization it is, and based on that we can output we can be sure like the probability will double and the DC will be 0 with a small rotation. Okay, so the by subtracting the sine square minus cos square components, the DC terms cancel out, resulting in a 0 background signal that is more sensitive to small changes around the bias point. Okay, uh, the next question is, in a fiber optic current sensor, the Faraday rotation angle theta is mathematically described as. Which one is the correct answer here? Any idea?
Option C.
Yeah, you are correct. We have already discussed about this one. Theta is equal to VBL. V means here worded um, constant V, and magnetic flux density is B, and interactional length is L, which we have discussed in the last few slides. You can see here somewhere. Yeah, here. Core mechanism, the Faraday rotation. Theta is equal to VBL. And for that we have discussed also the worded trade of tag crystal and the silica glass. Okay, so you are correct, at least you are guessing right. What is the significance of the non-reciprocal nature of the Faraday effect in current sensing? The rotation doubles when light is reflected back through the medium, allowing for the cancellation of reciprocal noise. It ensures that the light's wavelength remains constant regardless of the direction of propagation. See, it causes the worded constant to vary depending on the direction of the light. And option D, it prevents any length from being back reflected into the optical source. Which is correct here? The reflection one we have discussed already.
Option C.
Causes the vertex constant depending on the direction of light. No, it is not causing the vertex constant to vary depending on the direction of light. I do discuss the vertex constant only depends on the material, tag or silicon. Faraday effect we have discussed now how it is how the significance of the non-reciprocal nature of the Faraday effect in current sensing. So the we have discussed about the reflected back, light is reflecting back through the medium, allowing the cancellation of the reciprocal noise and doubling the rotation to theta. Okay, theta plus theta it is becoming once the light is propagating and reflecting back, So the Faraday angle or the theta here and here, it will couple and it will become 2 theta, but the noise plus the whatever noise angle is there, here also noise, sorry, here it will be minus noise, because plus minus noise, because the noise whatever is coming, the same, it will go back and it will cancel out each other, and that's why we are getting the cancellation of the reciprocal noise. Here we discussed, where we discussed, here, see, the reciprocal reflection configuration. Faraday angle positive plus positive noise angle, then once reflecting, then the Faraday angle is positive and the noise angle is negative, both becoming the final 2 Faraday, and the noise is 0. Okay, we have 2 more questions now. When designing a high sensitivity, I didn't click, yeah, I just take it, correct answer. When designing a high sensitivity current sensor using silica fiber, how is the low ordered constant V of glass typically compensated for? Option A, by replacing the photodiode with a polarization sensitive magnetic Hall effect sensor. Option B, by increasing the effect interaction length L using a multi-turn fiber coil. C, by using a high coherence laser to increase the magnetogyration uh, um, coefficient. And D, by operating the sensor at extremely high angular frequency omega.
Option B, sir.
Option B,
Length and fiber.
low is typically compensated for, yes. Option B, yeah, length. We are dealing with the length. You are correct. So if it is talking about the theta, which is V, B, and L, we know that B is constant, or we are going to sense it. So V, if it is low, if we can increase the L coil, or we can increase the length by multi-ton coil fiber, then it can be compensated. So if it is very large, so we can we can multiply the coiling multiple times. If it is a 1, it is a 100, so 100 times if you coil, suppose I am just giving example, so it will compensate it. So yeah, its correct answer is this one, option B. Doing good, yeah. So in polarization optical time domain reflectometry, POTDR, what information is analyzed from the background light to determine distributed perturbations? Option A, the total loss in power attenuation caused by microbending. B, the absolute shift in the Brouillon's frequency along the fiber length. And option C, the change in the pulse width of the reflected signal. And the last option is to evaluation of the polarization state or relative phase between components as a function of time. What's your answer? Correct answer here?
Option D.
Distributed percentage analyzed from backscattering up to distributed perturbation, evaluation of polarization state as a function of time. Yeah. So the POTDR tracks how the state of polarization of Rayleigh backscattering light changes over time, which maps to specific location along the fiber. Okay. So that's how we are getting the time dependent as a function of time the signal. And you are correct, the evaluation of the polarization state as a function of time. Okay. So yeah. So today we have finished all the question answers and the final modulating sensing modulator of the light for the sensing application, which is polarization. And today it was the last live session for us for this course, for this session. mm, yeah, so if you have any doubts you can ask me. I need to um, pack my bag also. I am going to France this today night, 2 o'clock something. So yeah.
Okay, sir.
Yeah, you have doubts, any doubts you have, you can ask me because this is the last live session, so
Yes.
I'll be free now. Yeah. Okay, then if you don't have any doubts I can just a second, what is the time, I'll check once. Yeah, 56 minutes. We'll wait for 5 minutes, 5 more minutes, after that we'll close the session. Okay.
Yes.
Hmm.
Thank you.
Yeah. If you have any doubts or any queries you can also ask me. um, there is a uh, discussion forum in the chat box is there on Swayam portal or NPTEL portal. You can go there and you can ask questions. I will reply there. Okay. Anything regarding the
Sure.
question answer or anything regarding the paper you want to ask, you can ask there, or anybody can ask there. So we can reply them and you and hope for your best. Exam should be very good and you should get the highest marks in this because you are a very dedicated person throughout the session.
Thank you.
Yeah. Okay, we'll wait for 5 minutes and after that we'll close the live session.